everyone, welcome to CLAT Build. In this video, we would be discussing about the conceptual parts of this very important chapter called time and distance. We see passages in the CLAT paper from this particular chapter very often. So let's jump to the concept of time and distance. Now this chapter of time and distance would be subdivided into three categories, which is general concepts, problems on trains and boats and streams. So let's start with the general concepts first. In the general concepts, we would be discussing four different things. Now the beauty of this chapter, time and distance, is we have only one single formula in this chapter, which is speed equals distance by time. Now if we analyze this formula, this effectively measures a particular distance that a moving object covers in a particular time frame. If we take an example, if we say that a car is moving at a speed of 40 kilometers per hour, this effectively means that in 60 minutes a car can cover 40 kilometers. So 40 kilometers is the distance part and 60 minutes, which is 1 hour, is the time component of it. So in the simplest of words, this is what this chapter seeks to measure. Now when we say that speed equals distance by time, from this formula we can derive that time is equal to distance by speed and distance equals speed into time. Now, so we have three different formulas, first being speed equals distance by time, time equals distance by speed, and distance is a product of speed and the time taken. Now, the latter two formulas is a simple derivation of the first mother formula of this chapter only. So, this was the first thing that we had to note in this chapter. Now, the second thing that we have to note is the unit of measurement. Usually in this chapter, the standard units of measurements are kilometers per hour and meter per second. If we have to convert a quantity from kilometers per hour to meter per second, we multiply that into 5 by 18 and we have to do the reverse, meter per second to kilometer per hour. Then we multiply the quantity 18 by 5. So if we take an example here, if we take 40 kilometers per hour and if we have to convert it into meter per second, then we have to take 40 into 5 by 18 meter per second. So let's find out how much that would be. So this will give us 100 by 9 meter per second. Hence 40 kilometers per hour is 100 by 9 meter per second. If we have to do the opposite, if we have to convert meter per second into kilometers per hour, then we multiply 18 by 5. So let's take another example where we have 25 meter per second and we have to convert it into kilometers per hour. We do this by 25 into 18 by 5 kilometers per hour, which would be, so this will give us 90 kilometers per hour. This was the third thing about unit of measurement that we had to note. The third thing in this chapter that we have to note is speed is inversely proportional to the time taken. So if we focus on the first concept that we learned, which is speed is equal to distance by time, speed and distance are on the numerators and speed and time are opposite of one another. Speed is in the numerator and time is the denominator. This means the third concept says speed is inversely proportional to time taken. What does this mean? This effectively means that if speed increases, the time taken reduces. This is fairly logical. So if we consider 2 points, which is A and B, and if the speed between these 2 points is 5 meter per second, then the time taken will be more. However, if we double the speed becomes 10 meter per second, then the time taken will reduce by half. So the mathematical implication of this inverse proportional relationship is if the ratio of speed is A ratio B, the ratio of time taken would be B ratio A, which is exact opposite of one another. Let's try to understand this using an example. So if the speed of two moving objects is 20 kilometers per hour and 30 kilometers per hour, if we find out the ratio of this speed, then it will be 20 ratio 30 or 2 ratio 3. If the ratio of speed is 2 ratio 3, the ratio of time taken by them to complete a particular journey will be 3 ratio 2. Now let's move to the second subdivision of this chapter, which is problems on trains. So there must be something extra in this chapter, which is why we have to study it as a distinct chapter, right? The extra part in this chapter is we have trains in this question and every train has a length of itself and a speed of itself as well. Now when we have objects like a man, a pole, a tree in question, then they don't have horizontal length. If you take an example of a human being, then we have vertical lengths and we don't have horizontal lengths. Like, it's too negligible to be taken into consideration. Hence, when we have objects like man, a pole, a tree, we ignore their lengths altogether. On the other hand, if we have concepts like a big train or a bridge, then it's too big to be ignored altogether, right? So if we have trains, then both the trains will have a length of their own. Now, two trains will have a speed of their as well. So we have a second concept in this chapter which goes by, if two trains are moving in the opposite directions, their speeds are added up. On the other hand, if they are moving in the same direction, the speed of the faster train is subtracted from that of the slower train. Hence, if two objects are moving in the opposite direction, we add their speeds, and if two objects are moving in the same direction, we subtract their speeds. So let's look at the general formula that we discussed in the starting of the class. This formula was speed equals distance by time. However, if we look at the speed in this chapter, if there are two trains, then we will have two speeds as well. And depending on the directions that they are moving in, we will either add the speeds or we will subtract their speeds, right? So instead of the S that we had initially in this question, we will have S1 and S2. Secondly, if we move to the D part, which is distance, then we will have length of both the trains into the question as well. So instead of that D, we will have L1 and L2 in this question as well, and time remains the same. So the initial formula of speed equals distance by time is now S1 plus or minus S2 equals L1 plus L2 by T. Now the third thing that we have to note in this chapter is the concept of overtaking of trains. Now if two trains are moving in the opposite directions, as we can see from this figure, then train A, which is moving from left to right, and train B, which is moving from right to left, we can say that train A crosses train B when the end part, which is the tail part of train A, crosses the tail part of train B, as you can see in this figure. Similarly, if there are two trains that are moving in the same direction, then when can we say that train A has completely crossed train B? This would be a situation where the back part of train A crosses the front part of train B, right? And this is also an explanation to the point why we add the length of the train. Now let's take the fourth and the final situation in this chapter, which is if two trains are moving, one is train A and the other one is train B, one is moving from left to right and the next train B is moving from right to left. In this case, they are moving in the opposite directions, hence their speed will be added up. Now, let's assume that the length of train A is 5 meters and the length of train B is 6 meters. And there must be some distance between these two trains as well. Let's take it as 50 meters. In that case, the general formula is speed equals distance by time. However, we will have two speeds in this question, which is S1 plus S2. And in the D part, we will have the distance between the two trains, which is 50 meters, and length of both the trains will also be added up, which is 5 meters and 6 meters. So the formula would look something like this: S1 plus S2 equals D plus L1 plus L2 by T, something like this. Now let's come to the third subdivision of this chapter, which is boats and stream. Now what would be the new part in this chapter? In this chapter, we will have boats moving in oceans or rivers. Now definitely a boat will have a speed of its own, which is owing to the motor or engine that has been attached with the boat. And second, there will be a speed of the stream as well, right? So in this case also, we will have two different speeds, which is speed of the boat and speed of the stream. Now let's consider this example where we have a boat, it has a speed of s1 and there is this stream which has speed of s2. Now the boat will either move from left to right or right to left, and the stream will also move from either left to right or right to left. Yeah, when the direction of the boat is same as the direction of the speed, let's assume that the direction of the boat is from left to right and the direction of the stream is also from left to right. This case is called downstream. So when the directions of the boat and the stream are same, it is called downstream, and we will have a speed downstream which is speed of the boat plus speed of the stream. In our example, speed of the boat is s1 and the speed of the stream is s2. So speed downstream will be s1 plus s2. On the other hand, in a situation where the direction of the boat is opposite to the direction of the stream, we call those situations as upstream situations. In this case, the speed upstream is speed of the boat minus speed of the stream. So this was it from the conceptual part of boats and stream as well. Now the final formula that we get in this boat and stream chapter is S1 plus or minus S2 equals d by t, because since we have one boat only in this question, we will only have one length. However, since the boat and the stream, both of them have a speed of their own, we will have two different speeds. So the final formula becomes S1 plus S2 if it is speed downstream, or S1 minus S2 if the speed is upstream, equals d by t. That was it from the conceptual part of this discussion on time and distance.